So after figuring out how to draw Lewis structures from chapter 3, the next thing that we want to do is to determine what a molecule looks like in 3D space, and this is basically what chapter 4 is about, determining the molecular geometry of particularly covalent compounds. So the Lewis theory, which actually allows us to write those Lewis structure, is great at basically predicting what atoms are of whatever elements are bonded to each other, how many electrons are involved in bonding, and how many electrons are not involved in bonding. These electrons, remember, are from valence electrons of these elements in the structure of the covalent compound. Now, what that doesn't tell us, however, is what the molecule looks like in 3D space. And using the VSEPR theory, a theory which is very simple, it just says that if you have electrons which are bonding, and if you have electrons which are non-bonding, regardless of whether they're non-bonding or bonding in a compound, they have negative charges and would want to repel other negative charges as well. Meaning bonds, electron bonds would like to repel another pair of electron bonds, or lone pairs of electrons can repel another lone pair of electrons, or a lone pair of electrons wants to repel also a bonding pair. And from those repulsions, because these electrons actually want to minimize, so the key word here again is minimize. So since these electrons want to minimize those electron repulsions, there is a given molecular geometry as a result of those electrons repelling each other. And that's what the VSEPR theory predicts. Now, to apply the VSEPR theory, it's very simple. So just start first by knowing the Lewis structure for the molecule. We've done that a lot for chapter 3. The next thing that you do is you do count the number of electron domains. Okay, so the term electron pairs is actually misleading. It's a term that is used in your book. But electron domains are basically how many either single bonds, double bonds, triple bonds, or lone pairs are around an atom of a molecule. So for example, this ball and stick model here actually is the ball and stick model for methane. Okay, methane has this Lewis structure. It has a carbon at the central atom, and hydrogens are bonded around it. Okay, this carbon has 4 electron domains. Okay, and all of those electron domains are actually bonding. So 4 of those are bonding pairs. Okay, and in particular, it's this, it's that, this, and that. Okay, now I did say earlier that structures like methane, for example, you also count the lone pair around that atom to be another electron domain. Okay, so methane also here has 4 electron domains. So this one's 4 electron domains. Okay, and pardon my handwriting. And it has 3 bonding pairs and then 1 non-bonding pair. Okay, now if you have, for example, a structure of or similar to formaldehyde. So this is the structure of formaldehyde. Okay, let's erase the other so that we can clear this out. Okay, so if you have the structure of formaldehyde, given that, you can actually see that there is 1 double bond. Okay, there is 1 single bond, or sorry, 2 single bonds. So So for formaldehyde, you actually have this time, oops, sorry about that. I'm still trying to figure out my stylus. So for formaldehyde, you actually have 3 electron domains, okay? And you have 1, which is a double bond. And you have 2, which are single bonds, okay? So it is important for this chapter, especially the first 3/4 of this chapter, that you know, number 1, how to draw a Lewis structure, and number 2, how to count these electron domains. So again, a single bond is counted as 1, double bond is counted as 1, triple bond is counted as 1, and a lone pair is counted as 1. Now, we're distinguishing here lone pairs from bonds because lone pairs, as you remember, let's say for example, this formaldehyde, what's actually missing in this Lewis structure is the fact that you have 2 electron pairs around oxygen, okay? Now, those electron pairs are actually occupying a lot of space, okay? Let's say for example, that electron pair occupies that space, and then this other electron pair occupies that space, okay? So this space occupied by those electron pairs are much bigger, for example, compared to this space occupied by these 2 bonding electrons, okay? So, and again, since all of them are negative charges, basically this lone pair on the left and this lone pair from the right want to be as far as possible from each other. Now, they don't want to be near these 4 electrons in this double bond, and that double bond doesn't want to be near this or this pair of electrons in the single bond. And that's what VSEPR theory predicts. So the VSEPR theory predicts that lone pairs will repel lone pairs at a greater degree, okay? And lone pairs can also repel bonding pairs. I mean, they're still electrons anyway, but the energy penalty compared to lone pair repulsions is lesser. And lastly, bonding pairs themselves can repel another bonding pairs. So let's say for example for methane, or sorry, ammonia. These electrons will repel each other, okay? And this lone pair, which again is occupying a lot of space, wants to repel that bonding pair, wants to repel that bonding pair, okay? So right now, they are at 90-degree angles to each other. But if we orient all of those bonds such that this heavy line denotes that this NH bond is moving out of the screen, and this dashed line denotes that this NH bond is moving into the screen, we end up with this geometry which looks like it's tetrahedral, okay? It looks like a tetrahedron, okay? Now, this is actually the electron pair geometry of ammonia, meaning if you were to imagine, for example, this lone pair to be a separate bond, again, it's not an actual bond, this lone pair associated with ammonia. If you were to imagine that as a bond with a big blob of element attached to ammonia, then this is what it should look like in 3D space. Now, that is different from what chemists and scientists usually like to report more. What they like to report more is the molecular geometry. The molecular geometry is derived from the electron pair geometry. It doesn't really consider the lone pairs. And basically, if you take those lone pairs out of view without, of course, actually removing them from the Lewis structure, then this will be what ammonia should actually look like in space. And for ammonia, this molecular geometry is trigonal pyramidal. But let's get simple first and look at central atoms in which we do not have a lone pair. But again, everything so far is VSEPR theory will actually tell us that electrons just like to repel electrons, other electrons, just because, again, they're all having negative charges, or they all have negative charges. All right, so if you have two electron domains, and that's usually for beryllium, but there are other cases too, such as CO2. Okay, let's write the structure for CO2 because you're given here actually beryllium difluoride. So carbon dioxide has this Lewis structure. Okay, so as you can see around carbon, there's actually two electron domains. Okay, both of those are double bonds. If you have two electron domains, and again, no lone pairs, I know that the title actually says single bond pairs, but CO2 actually applies to this one as well, then you have a linear configuration. So if we don't, so beryllium difluoride has this Lewis structure. Beryllium difluoride. I'm not going to include lone pairs around fluorine anymore, because for Lewis structures, or rather for the VSEPR theory, we're only considering the central atom anyway. So the structure for, let's erase, just erase this arrow. Lewis structure for beryllium difluoride can be written like that, or it can also be written like this. Okay, nothing stopping me from writing it like this. Now, if we have the structure at the bottom, so the bonding pairs, beryllium fluorine and beryllium fluorine bonds, are actually 180 degrees apart from each other. Whereas for this structure, they're 90 degrees apart from each other. So those bonds actually want to be as far as possible from each other. So beryllium difluoride in space will actually not have this structure, but will instead have this structure, which is linear. Okay, now, so that is again the case if you have two electron domains and you don't have a non-bonding pair. If you have three electron domains, you have, and again, no bonding pair in any of them, they're all just single bonds, or they're just bonding domains basically. You have a trigonal planar molecule. Trigonal planar molecule looks like this, SBF3. So the word planar just means a triangle pressed flat on a plane. So BF3, again, we can write the structure like this. Okay, so if we write the structure, these two angles are at 180 degrees apart from each other, but this one's 90 as well as the other one. So in order to minimize these repulsions, this bond on the left and this bond on the right will be pushed a little bit clockwise and counterclockwise respectively, and we'll end up to have a 120 degree angle from each other. And as a result, all of those bond angles in a trigonal planar molecule will actually end up to be, actually 120 degrees from each other. Now, if you have four electron domains, you have a tetrahedral molecule. We have here carbon tetrafluoride. So carbon tetrafluoride has four electron domains, and each bond angle are actually 109.5 degrees from each other. So it's important to remember actually all of these bond angles. And again, this is only if none of the electron pairs are lone pairs. And then if you have five electron domains, you have a trigonal bipyramidal molecule. The example will be phosphorus pentafluoride. Keep in mind that phosphorus here violates the octet rule, and that's okay. And then if you have, but basically the trigonal bipyramidal molecule is characterized by two trigonal based pyramids, or two pyramids with a triangular base pointing opposite each other. And then an octahedral geometry in which you have six electron domains is basically characterized by a square pyramid, okay? Meaning a pyramid with a square base, and you have two of them pointing at opposite directions.